And you could come closer, further back, whatever's comfortable for you guys or whatever. I was thinking about putting this table there so you guys can use the table, but I kind of needed a table. I could do that. I don't know. Maybe we'll try that next time. Yeah. Whatever. It's too late now. Okay, homework 18, page 262. We are jumping to section 4.7. We'll probably return to 4.4 at some point. Maybe, and we might touch it briefly. But sections 4.5 and 4.6 we probably won't get into. You could look at those. It's not that they're not useful or interesting. It's just that in every class I've taken, and you know, I tutored calculus for over a decade at the college level, and I've never seen anybody cover these sections or anything like it. So if we had more time, I'd do it. It would be cool. But since it's not really touched on in general, or like regularly, I'm not going to go into it so that we could get into other cooler stuff. So 5 and 6 probably won't touch. We'll probably return to 4.4 at some point. But right now we're going to get into 4.7. I'm going to say a couple things here. Number 51. Here's a huge hint. Like, if I'm giving you this, if I'm telling you this is equal to this, then maybe what you're working on might have an M in it. It might have a B in it. It might have an A. It might. No, why am I doing it? Why would it look like this? Well, that's a huge hint because, yeah, something in something you're working on should look like that at some point. So that's a huge hint because you might look at that and go, I'm not sure what to do with this at all. And if that's the case, it's just the case. This might help you get to the right track. One more thing. So in the section itself, oh, and another thing, if at any point you're doing these and you're like, I'm not sure what to do, maybe try reading this section. They might have an example that would help you along with part of it. We're not going to be able to get through all of that, but the material's there. So read it, and if you're struggling with something. Part of the stuff that we're not going to cover is applications to business and economics. It's all right there if you want to know more. You don't really need to in order to do this one. This is the only thing that has economic stuff in it, and in particular it says marginal cost. And all you need to know is that the marginal cost is the derivative of the cost function. If you want to know more, it's right there. It's just the rate at which, marginal cost is by definition the rate at which the cost changes with the input variable being the product, whatever, or that sounds weird when you're in a math class, but the product, the thing that you make. Yeah, right, okay. Okay, so today we're doing optimization problems. It's my favorite stuff. Well, one of my favorite things in calculus to do. Now, if you guys recall, in Algebra 2, I gave you guys a checklist for optimization problems. If you go on YouTube, the Algebra 2 lectures playlist, Algebra 2 lectures, Lecture 45, optimization. I'm not going to write it out. Optimization problems, I think is what the title is. If I remember, I'll put a link. Put a link in the bottom. Link down there. Got to tell myself to do that. So I'll try to remember to put a link to it on this video. But it's in the Algebra 2 lectures playlist, lecture number 45, optimization problems. I had a list of steps, basically an algorithm for doing any kind of optimization problem. And I think in that video, maybe I didn't say that, maybe I did or didn't say this when I did it with you guys, because the video was a year before that. But these are the same, I said in there that these are the same steps you'll take when you do optimization problems in calculus. And it's almost true, it's almost exactly the same. So this is what it was in this video, in Algebra 2, this is what we're doing. The first thing you do, so an optimization problem, if you guys remember, you're trying to find the most something. Like you have some kind of thing and you want to minimize the cost. or you want to find how can we get the most profit in something like that. Or you want to fence an area, you have a lake or a river, and you want to make a fence given a certain amount of, what are they called? Certain amount of fence, certain perimeter, and you want to maximize the area. You guys remember this stuff. These are called optimization problems. And the only way we could tackle optimization problems before was if if the thing that you're trying to optimize was a parabola. Because with a parabola, its max or min occurred at its vertex, and we had a formula for the vertex, or we could derive where the vertex is, and therefore we could do it. Well, now we have some bigger guns, right? We don't need a formula to find a vertex. If we want to find the max or min of a function, what do? Exactly, right? And so, guess that one of these, somewhere in the steps, we're going to modify that, right? So this is the old thing. The first thing you do is draw your picture. That's still true. First thing I want you to do is draw a picture when you're working on these. The second thing we do is you identify, ID, the quantity you want to optimize. So like for instance, with the river and the fence, the quantity you want to optimize is the area, right? That would be the thing that you're trying to find a max or a min for. So what we mean by optimize. Now, here I'm going to add on a little bit of that because, and this is the tricky thing, is that it's not going to be exactly this way for everything. Okay, and we also saw when we did these in Algebra 2 that not everything lends itself to following these steps exactly. Use your brain, right? Like if you could see a cool shortcut, do the cool shortcut, but this is kind of the foolproof way if you're not quite sure what to do. But there's kind of a second part to this one. And it's not for every single one of them, but it will be good to also, in this case, ID the variable. The thing that you can change, right? So like in this thing, and it doesn't really, you see this is why in this type of problem, you have, let's call this length x, this length y, then your area would be x times y, right? Kind of going along with that. You really don't need to ID a variable here because it's like, well, I guess, what do you mean by variable? They're both variable, they're both the things that could change. You'll see in the example that we're going to do here in a minute what I mean by that, by this part of the step. It should become more clear what I mean. Okay, so 3. The third step was write a function whose output is the quantity. The quantity that you want to optimize, this quantity that we're talking about. And here I'm going to add, and whose input is the variable. If that, so these are kind of parenthetical, because certain problems will lend itself easily to that, certain problems won't. The first one we do will lend itself to that very easily, and having it written like this, or having it in your head like this, will help, especially with this first problem, which is a doozy, okay? So just, this should go without saying, but it might be the case that you can't get it down to one variable. Like this, right? This is not a function of just purely x. This is a function of both x and y. We don't know, and the same way we didn't know back in Algebra 2, we still don't know how to deal with functions of two variables. So, this is where steps 4 and 5 came into play. You write a constraint function or equation. Write a constraint. Now in this case, with this, it's usually given like that the farmer has 100 feet of fence, right? A total of 100 feet of fence. So that the perimeter is 100. And so then the constraint would be, well, I guess this is y and this is x. Whatever y plus x plus y is, y plus x plus y, or in other words, 2y plus x, that constrains, right? That you can't just let x go off to infinity. You can't have y go off to infinity, right? There's something that constrains what you're doing. We call that the constraint equation. Okay, so in this case, that's your constraint for this guy right here. It might be the case that if you get to step 3 and you can already have it down in one variable, see right here we're not in one variable. A is a function of two things, x and y. We don't know how to deal with that yet. So we need to drop this down to a function of one variable, and that's where steps 4 and 5 come into play. But if you're at step 3 and you have a function of one variable, then we're going to skip steps 4 and steps 5 because why? That's not the point. Once you have it in one variable, you'll see what we're going to do. In fact, I bet you could guess what we're going to do with a function of one variable and you're trying to find its min or its max. Okay, so step 5. Use the constraint to turn your function, and that's from step 3, your function from step 3, from 2 variables to 1 variable. And so here, in other words, you solve for one of the variables and substitute it in. So in this case, I guess we could get y by itself. It would be easier to get x by itself, but since I already wrote a of x, I'm going to do it this way. I'm going to say, okay, 100 minus x equals 2y, so that y equals 50 minus a half of x. Now, I plug that guy in for y, giving me x times 50 minus 1/2 x, like that. Now we have turned our function, the function whose output area is the thing that we're trying to optimize. In this case, we want to maximize it. And so we've turned that function into a function of one variable. Now, I'm not gonna get rid of this. I'm just gonna make a little bit of room here. And yeah. Now, this is what it was. In the lecture, I said 6 is graph function. I'm not saying to throw this step out, but oftentimes the function that you end up with is something like this. And you're like, I'm not graphing that. Just, the reason why we graphed it before was because I wanted you to graph as many parabolas as possible. If it helps you, graph it, please. Don't just throw it out for no reason. I mean, if you want to graph, anytime you want to graph a function, I'm not going to stop you. And so then 7, the 7th step was find, and this is how I wrote it on the board, find the minimum or the maximum, and then I put, that's the vertex of the parabola. As you can see, this indeed, we've done this one before. This is a parabola, you know, it's a downward-facing parabola because of this right here. This is the same thing as minus 1/2 x squared plus 50x. You could graph that guy. He looks like this. He goes through at 0 and whatever, I guess 100. You know, and it happens to be halfway between it because it's a vertex. Well, we don't have that luxury anymore, okay? And so, so now, I guess we've already solved this, so who cares? So, these are out. And we have a new step 6. Which, now that we have a function of one variable and you want to find its min or its max, what do we do? Take the derivative. Yeah. Take derivative, set to 0. Set to 0, and solve. Then, step 8 is going to be our new step 7. Old step 8 is new step 7. Use the function and constraint, if you have it, to find the desired stuff. Might be asking, that question with the area could have been, where should he put his fence posts? In which case you have to figure out, okay, if that's 50 and that's half of that's 25 and that's 25, well then whatever, right? You use whatever, or maybe it asks what is the total cost of the fence that he's going to need to buy. And so you need to say, well, if it's 100, well, I guess if it's 100, that's a bad example, but you know what I'm saying, right? It could have said, what is that maximum area? In which case you find where that occurs and you plug it back into your area function and you find the area, okay? Everybody got me? This is just review. Again, this stuff is out there, or this stuff is on the, YouTubes, okay? So I'm gonna get rid of this. I didn't officially state what homework 18 was. I stopped once I said it's section 4.7, but there it is. Okay, and that's a 67 right there. That's a 7. Okay, here we go. This is one of my favorite problems in all of, I would say, not just calculus. This is one of my favorite problems in all of mathematics. And I'm so glad we get to do this. Unfortunately, it's very poor timing. And as you'll see in a minute, there's some stuff going on in the world right now, which it would seem like, oh, dude, that's bad timing. Well, I've planned this for a long time, and I'm just going to go ahead and do it. So here's the setup. Here's the setup. You are on the bank of a river, right here, with your canoe. That's a canoe. The river is 30 meters wide. From your point here, 900 meters down the river. So I'm not writing this out. So we're doing step 1 right now. I'm writing it out as I'm saying it. I'm drawing a picture of what's going on. 900 meters down the river, and we're going to pretend it's a still river, whatever. We're not going to, that's, as you'll see, that's not part of, that's, the current of the river does not come into play. In fact, you can pretend it's a lake, and it's just it's shaped like this. So 900 meters down the river is your house. You look and you see that your house is on fire. Bad timing. So, you know that you could run. You can run at 6 meters per second. But you could only row your canoe. Yeah, it is. You're a freak of nature, right? Okay, so you could run at 6 meters per second, but you could only row at 3 meters per second. Also pretty fast. You're a hoss. You should probably, yeah, anyway. Here's the question. At what angle should you row across the river to minimize the time it takes you to get to your house? Isn't that a great question? So here's the question. So now as I'm reading this, I'm like, okay, well, let's just imagine I'm going to row at what angle, right? So that's the question. At what angle? And should you row, right? And when it's given, I read this in a calculus book a a long, long time ago, and it's stuck in my head ever since. I only read it once, and I just love this question. And of course, they say with respect to measured this way, blah 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 blah. And then when you give it as a word problem, you say east and west and all this stuff, so you could draw an accurate picture. But I've already drawn the accurate picture, so we have enough information here. At what angle should you row to minimize what?
The time.
The time it takes to get home.
So.
Okay. So, we've done step 1. Now let's do step 2. We identify the quantity we want to optimize.
The
Time is what we want to optimize. Now, what's my input variable then? And you see, this is where the second part of it comes in.
You want the angle should be the output. Wait.
Are we trying to optimize the angle? Are we trying to find the minimum angle?
Yeah, optimize the time.
See, we're trying to optimize the time. So we want, okay, so we're just IDing the quantities now. We're not going to the next phase. So time is to be optimized. Right? Time is the thing we want to optimize. And so what is the variable here? So what is the thing that can change?
The angle. So
The angle. And so the angle is variable here. And so this is what I mean. Like, this is one of the questions that doesn't have a constraint. Here we know, like, and so here's step 3 is write a function whose output is time. So in other words, we want a t of where the input is the angle that we want. That is our goal right here now. Is to find a function whose input is angle, because that's the thing you could change, and that's what I mean by variable. Identify the variable. The only thing that you can change. And in this case, this is weird, right? Because it's asking you at what angle. And so you think, the angle's the thing I want to optimize. Nope. Because to minimize the time, so our output needs to be time, and it has to be a function of angle. But as of right now, they haven't given us any times, and we also, like, all we have are rates, and it's not really there yet, distances. So, can we get, given a distance and a rate, can we get a time?
Yeah, distance equals rate.
Distance equals
Rate times
times time. So time is equal to distance over rate. But now here's the thing. You might think, okay, so I'll just get those distances together and then divide by rate. And so I'll have some kind of distance divided by rate as one thing. But we have two different rates, don't we? You could run faster than you can row. So what we're going to want to do is break this into two distances. I'm going to call this distance here, the distance that we row, I'm going to call this D1. This distance that I'm going to run along the shore is going to be D2, or the riverbank here. Okay? And so then the total distance, and this is tricky here. You might think, oh, okay, so then the total distance, the D thing that I want, is D1 plus D2. So I'll get my D1 plus my D2. I just divide that by rate and I get my time. And so you go, rate, and there's time. But no, there's different rates. So what do we need to do?
R1 and R2.
Yeah, exactly. So I'm going to go ahead and call this, which one's R1, which one's R2?
Well, you're rowing first.
Rowing, so that's R1, and this one's R2. So, the same way that we would, if you're doing this, you know, just writing out, well, then the total distance is D1 plus D2. Same thing here. My total time is, I'm going to call it T1 plus T2. Okay. But T1 should just be that first distance divided by the rate, right? T1 should be D1 divided by R1, right? Okay, so here we go. D1 divided by R1. And then similarly, d2 divided by r2 gives you the second time. Now, here's the hard part. We need to get those distances in terms of theta. And right now, the only theta I see is right here. And so,
It's a triangle. We could find the hyperbola. Wait,
yeah. So let's play with this a little bit. Let's just work on D1. Let's just pretend here that all I had was this information right here. Theta D1. Is there any other length that I'm given?
30 high.
Ah, we know it's 30 high. So, what trig function relates those two together?
Sine of theta equals 30 over d.
Sine theta equals 30 over d1. So d1 is the thing that I want. What do I do?
So d1 equals sine. Yeah, 30 over d1 equals 30 over
That's how I would write it too. You could say, divide by sine theta, that's the same thing as 30 cosecant theta. What's the derivative of cosecant? Yeah, right, exactly. So I don't even bother with that. So I'm gonna say, okay, d1, and what's r1? 3. So I'm gonna go ahead and write this explicitly here. The d1 is on top, 30 divided by sine theta, over rho is r1, so 3. We'll clean him up in a minute. Now, d2. d2 is from here to here. In other words, from here to
Oh.
here. So how do we find that?
Like
distance?
900
900.
minus d2 is the tangent of.
Okay, okay. Here's the thing. Here's the thing now. It is going to be whatever 900 minus this length. Let's call that length L. Let's call it little l. We'll call it capital L. Okay. So you're telling me d2 is 900 minus L. We need L in terms of theta.
Tangent of theta equals.
That's so different from how I did it. That makes so much more sense to do it that way. I wish I would have thought of doing it that way. I said cosine theta is L over d1, so that d1 cosine theta equals L, and then 900 minus that, and you'll see it's going to give us the same thing. But anyway, here. So let's do it your way. I like your way. So you said tan theta is what?
30 over L.
30 over L, so that L is 30 over tan theta. Now watch this. I'll go on this side. That's the same thing as 30 sine cosine, yeah? Right, because divide by tangent, that's right. I just have to make sure here. That's sine over cosine. And so that flips, the cosine comes up into the numerator. What's d1? I wrote it somewhere. There it was. I erased it. It's the same thing as 30 over sine times cosine. Is that the same thing as that?
Yeah.
Yeah. And so we could write this, and I would suggest that if you did it this way, and you're about to put that into whatever, into here, so that d2 is 900 minus L, it's almost always easier to get everything in terms of sines and cosines. Yeah. So I would rewrite that as that anyway, and say that's the same thing as 30 cosine theta over sine theta right there. So there's d2. So plus d2 is 900 minus 30 cosine theta over sine theta, like that, yeah? All over, thank you. R2 is 6. Now let's clean this guy up. Okay, I'm gonna get rid of this stuff, And if you didn't think to do that and you had 30 over tangent, everything will be fine. You'll eventually have to take the derivative of 1 over tangent. It won't be bad, trust me. Like there's hardly many wrong ways of doing this, but it's like if you have the right things, if you write it as cosine or 1 over cosine or secant, you're fine, right? So okay, now that's the hard part. Now here's the question: do I have t in terms of theta?
Yeah.
So in other words, I've dropped my optimization function is a function of 1 variable. So that's what I want. I don't need to worry about steps 4 and 5, which were write a constraint function and then use the constraint function to drop my 2 variable function into a 1 variable function. We already have a function of 1 variable. So now we could just skip to the bread and butter of this. But I'm going to rewrite this a little bit. I'm going to clean this up and say that's the same thing as 30 over 3 sine plus 900 over 6 minus 30 cosine over 6 sine. Which I could clean up a little bit more and write that as, how about 10 over sine. I'm going to do this first. Minus, let's see, the 30 over 6, is that 5? 5 on top? Yeah, 5 cosine. 5 cosine theta over sine theta. Now, plus 900 over 6, I believe, is 150. Let's see. I did long division on it last night. I was like, that's got to be divisible. And I did long division to do it. And yes, indeed it is. Okay, so. Is that where I am? Yep. Okay, so here we are. Step 4, check. I'm going to go ahead and get rid of this stuff here and say, now we have a t of theta. The output is time. Because it was, all of these came from a distance divided by a rate, which gives us time. So the output of this is time. And it is a function of 1 variable. That variable happens to be theta. That's what we want. And so that will give us the thing that we're looking for. So since it's a function of 1 variable, we don't need a constraint function. We don't need to drop it into 1 variable because it's already in 1 variable. So what do we need to do to find the min or the max of this?
Take the derivative.
All right. So we're going to set it equal to 0. So I'm going to take the derivative. T prime of theta equals
1/10 times.
and so this is how I'm going to do it. I'm going to think about it as sine to the -1. Take the derivative of the outside stuff. The -1 comes down and it goes to the -2. Then you multiply by the derivative of the inside stuff, which is cosine. So I could rewrite this as minus 10 cosine over sine squared. Now, if you had done this, as instead of written this, it would have been cosecant, 10 cosecant theta, you take the derivative and you'd find that the derivative of this, it's like -10 cotangent cosecant. And you'll see in a minute why having it in terms of sines and cosines, just keeping it in terms of sines and cosines is almost always easier. But I'm going to go ahead and leave this right here, because that's what that is. Cosine over sine is the same thing as cosine over sine times 1 over sine, right? Cosine over sine squared is the same thing as that,
Yeah.
which is cotangent times cosecant. Okay, so just something to note. Okay, now this is one of the scenarios where I would actually use the quotient rule, right? So we have -5 is going to stay out front. Now, it's the derivative of the top first, right?
Yeah.
Okay.
Yeah.
So what's the derivative of cosine?
Negative.
Negative sine, leave the bottom one alone. Subtract off, leave the top one alone. Multiply by the derivative of the bottom, which is cosine. Square the bottom. Now there's a few ways you could write this. One thing I noticed right off the bat is there's negatives and a negative. If I pull the negative out,
There's no more negative.
then there's no more negatives, and I'm left with a sine squared plus cosine squared on the top,
No, that's just.
which is just 1.
So 1 over sine squared.
1 over sine squared. So, or how about 5 times 1 over sine squared? Or how about just plus 5 over sine squared theta?
And the 150 is
And what happens to the 150?
gone.
Okay, because the function f of x equals 150, its slope is 0. And so, I've taken the derivative, what do I do with it?
Set it equal to 0.
Set it equal to 0, okay? Because I'm trying to find a min or a max here. Okay? Now, here's the cool thing about leaving it in sines and cosines is, well, okay, so I'll just go, if I were just presented with this problem, I'd say, well, there's positive, that's negative, why don't I just bring him over here?
Just divide or multiply by sine squared.
Exactly. You have the same thing in the denominator. And that's another thing I just want you to see. So, as you're well aware, if your function looks like this, and you take the derivative of it, then the derivative of that looks like there's something up here, and it's whatever, it's the derivative of whatever's in here. And then all of this stuff appears on the bottom. And if you're optimizing something, or you're trying to find a min or a max, the thing you're doing is setting that equal to 0. What can you do to both sides of that equation to make your life easy?
Square both sides.
Thinking way too hard.
Oh.
Like if I have
5.
x over 5 equals 0, or x, I don't know, squared plus 3,
Multiply by the
35.
bottom.
Multiply by the bottom, right? You could just clear the bottom. Multiply by that and it's gone, right? The only thing you need to worry about is, well, you got to make sure you're never dividing by 0. Okay? And so we'll come back to that in a second, but right now I just want to get to the chase, and we can do that a couple different ways, but I see I have a derivative equal to 0. Oh, and there's the same thing that I can just kill the denominators by multiplying both sides by sine squared. Do that over here, do that over here, to kill those. And now I have minus 10 cosine theta plus 5 equals 0.
Negative 1. Wait. No.
Yeah, well, this is, I mean, I see what you're driving at, but this is how I like to do it, so I don't mess that up, because you just messed it up. I gotta make sure my sign here. Now,
So divide by 10.
divide by 10. We get 1/2 equals cosine theta.
And it's like pi over 6, I think. No, pi over the other one, pi over 3, I think.
Yeah, I think you're right. So which triangle is going to help us?
The 1, 2, root 3.
And what's this angle, and what's this angle? This one,
Is pi over 6.
pi over 6. This one's
Pi over 3.
pi over 3. And so, which one of those gives me cosine?
Pi over 3.
Yes. So, theta is pi over 3. But remember, it's not the only time that cosine equals 1/2. In fact, cosine is equal to 1/2 infinitely many places. So now this is where, and I didn't write this down explicitly, but you want to do this. You have to stop and think. Wait a minute, wait a minute, wait a minute. First off, let's take care of that sign. What happens when, where is sine equal to 0? Because we can't be dividing by 0. I want to make sure we're not doing that.
Pi over 2 plus sine.
No, pi plus 2.
So wait a second, sine does this.
Pi plus 2.
So yeah, so sine is equal to 0 here when theta is equal to 0 and when theta is equal to pi. What happens here if theta is equal to 0?
Then you're never.
You never. And what happens here if theta is equal to 0?
You're also.
This is going to blow up, and your time will be infinite. You don't want to take an infinite amount of time to get to your home when it's on fire, right?
Pi.
Now, what's the other time when it's pi? What happens if theta is pi?
You're also.
You're also never going to get home, right?
Going the wrong
So now what we could have done at the very beginning, and one thing that's nice to do whenever the question is something about angles or you have any kind of angle, is kind of see, where does this make sense? obviously theta needs to be bigger than 0. And it probably, at the worst case scenario, you're not going to row backwards. You're not going to go that way to optimize your time to get this way.
But then there's more time than
Well, so, hold up. So, theta, so one thing we could have done at the very beginning is say theta should be a number between 0 and pi over 2. Or if we're doing degrees, 0 and 90 degrees. Because it doesn't, and it might be the case, if you row really, really, really slowly compared to how you run, you can imagine, right? And you see how this works, right? Because if you row the entire way, well, if you row faster than you run, then that would probably be the answer, is to row the entire way, right? Like, in fact, if I would have just given you this problem and said, you row at, or rather than row, maybe you have a speedboat, and it could go 10 meters per second. Well, you'd say, well, it's probably quicker to just do this. Although we wouldn't know, because, well, yeah, actually you would, because that would be the shortest distance, right? The shortest distance between 2 points is a straight line. Hopefully we'll be able to prove that later this year. And
Can we not prove
extra credit, prove it. So, I mean, it's obvious,
that? Yeah.
but is it? So, yeah. How do you formalize that? That's the question. So, and then on the other hand, so these are kind of like your bounds, right? You say, well, obviously it has to be bigger than that. You're not going to go past it. So whatever that happens to be, we could get a better bound here. And it also makes sense. So if you could row way, way, way faster than you could run, it would make sense that this would happen. But since you could run faster than you row, another problem here is if you go straight this way, you're also maximizing the distance that you're going to go, right? You minimize the distance by just going in a straight line, but the speed is the problem here. Maximize your distance by going this way, and obviously you don't want to maximize your distance if you're trying to get somewhere. So there's a sweet spot somewhere in between, and in this case, it happens to be here at pi over 3. Pretty cool problem, huh? I like this problem. And then when I read it in the book, I was like, "This is a great problem." And like they said, the way it was stated too, is like, "You look and see, your house is on fire." And so, yeah. Any questions on this? I think there were a couple more things I wanted to say. So, yeah, I think this is a great problem, and.
Hopefully you can do this problem fast enough.
And that was one of the things I wanted to say. Now, in the real world, you'd probably just go 45 degrees.
Yeah.
Because you're not thinking, you're like, I need to get there. But you know, as you're doing it, it's like, if I row this whole way, it's not going to, and you just kind of make your way across, right? But you also know, if I go straight across, it's going to maximize the distance that I'm running. And so if you just guessed pi over 4, you wouldn't be that far off. But yeah. But then again, you'd have to know. So please, if this ever happens, just don't worry about doing this.
Well, now remember.
Because you minimize the time of getting home. The correct answer is don't do this problem. Just go, right? Okay. Because how long did that take? But yeah. So now let's say there's a follow-up question. Here's the follow-up question. I need to keep that there. We got pi over 3 right there, so I'm going to erase this stuff down here. So of course the follow-up question would be, how long does it take? How long does that take? Or what's the fastest it could have just said that. What is the fastest you could get home, right? But here we go. How long does this take? What do you do?
So, plug in pi over.
There you go, right? Plug in pi over 3. Now here's the thing about this. Did I say this here? Yeah, let me just do this first. So when you plug in, we're not going to do it all, but if you plug in pi over 3, you get pi over 3, that's 10 root 3 over 2 down here, minus 5 times a half. Another root 3 over 2 down here, plus 150. And that works out to 158.66. 158.66. What's
Meters per second.
No,
Right.
just
Time.
Oh, time.
Seconds.
It should just be seconds because we did meters per second, right? And that's the thing, right? Remember, we took distance over rate, which the distance was in meters, and it was over meters per second. So this worked out to meters times seconds over meters. And so yes, my time function was indeed in seconds. Good, okay? That should be the way that it works. We could have checked that, right? This works out to 2 minutes and 38.66 seconds.
It's pretty good.
That's not bad. You'd have to run really fast. Okay. How do we know that this is a minimum and not a maximum?
Oh.
Like we went through all this problem, right? We went through this whole thing and we got this answer, and it makes sense, right? Because you know if you go this way, you're maximizing your distance, so it can't be that. You know that if you row the whole time, you row slower than you run, and it makes sense that. So it makes sense that we got something pi over 3 that is in the range that we're looking for. It's in the domain that we're looking for. But how can we be sure that it is indeed a minimum?
If we graphed the.
That's one way of doing it, and that's what I was going to get at. But what's a way that you could do it just analytically right here on the board, if you wanted to know whether it's a min or a max?
Something a little bit
Well, we have
after
the
it and
little-
see if it goes.
No.
Yeah, it's
Second, to take
greater
the
than
second derivative, you would take the second derivative, plug in pi over 3, and if it is,
greater than
if it's greater than
Concave
0,
up.
then that means it's concave up
which
and
means
it's
it has
a minimum. Right. So that's what you would do if you wanted to prove that it was a minimum. I probably don't need it. There's going to be one or two problems where you'll have to do that. But in this problem, obviously, this was the only one because we found, right, it was 1/2 equals cosine theta, right? And we could see that cosine theta is 1/2 only in the first and the third quadrants, right? So in other words, here's pi, here's 3 pi over 2 right there. And so obviously we're not going to row down this way, right? We're not rowing back that way. So it's like, well, everything works out, and this is the only way it works out. It probably didn't maximize this because obviously I can maximize the time by just going straight down there. So it's kind of like, and so what does that mean? So Noah beat me to the punch. If you graph this, this becomes much more clear. And this is what I would say to do. So actually, so what I'm telling you to do for these homework ones is sometimes it's obvious. There's only 1 0 in the range that I'm looking for. Or rather, the derivative only has 1 0 in the range, or I'm sorry, in the domain that I'm looking for. So it's gotta be the min, right? It can't be a max. And just looking at this, like that would minimize the time. Right? I mean, it would be longer if you rode this way. It would be longer if you rode that way and went all the way across. So it makes sense that this is less time, so it's got to be a minimum. But if you're really curious, you could graph, just go to Desmos, graph t of x, and what it looks like is something like this. And, like, okay, what does that mean? Well, and then again, if you look in your, you zoom in down here and you see, yes, indeed, there's that this asymptote occurs at a pi over 2, which makes perfect sense. Or is it a pi over 2 or it might be a pi? Where was it? No, it was a pi over 2. I think. Actually, I don't know if I really looked. It might be a pi. Who cares? That's not the point. It actually might have been a pi. I didn't look. I just assumed it was a pi over 2. It might be pi. And that would make sense. Because it's infinite if it's 0, right? If your theta is 0, then it would take you an infinite amount of time. And of course that blows up there. And if it's pi, you're rolling that way, it would also take you an infinite amount of time, but negative time, whatever, who cares, right? And so you could just see that the only thing that makes sense is this, right? Or you could graph it and see that, yeah, when you plug in a pi over 3, you get a min right there. Actually, I think it is pi over 2, which is interesting. Very interesting that one does that. Huh. Oh, that's weird. Okay, anyway, I could be wrong. You could graph it and figure that stuff out. I wasn't really looking for that. But you gotta think, but if you do this, you gotta think about the domain for your function. Because you might say, well, what about this guy? Well, that doesn't make much sense, because that's just like, whatever, however, 7 pi over 3, right? You've wrapped around or whatever. And so, yeah, okay. Okay, so that's that question. That's one of my favorite questions of all time. I think it's great. Any questions on the question before we move on? Okay, there we go. So this homework's going to be really tough. And hopefully there'll be enough time for you guys to do it. Tuesday should be enough. This is only however many problems it is. It's not that many. But they are tough. One type of problem you're going to see a lot, well, you're going to see at least once, is number 12. And it's a box with a square base, an open top. Must have a volume . 32 centimeters cubed. The actual one is like 32,000, and I'm like, I'm not doing that. it's 32. Find the dimensions to minimize the material used. Find the dimensions which minimize.
So,
Step 1.
draw that.
Draw it, sure. Okay, so here's a box. And we know that its base is square. That's nice. Let's give this length a name.
Oh, like, oh.
And since it's a square base, that's also x. That way. Now the question is, what should y be, basically? Right? We could think about it that way. There's y. Okay, so
So the volume is, so x times x times y.
wait a second. So step 2. Identify the quantity to be. What is the quantity that we want to optimize?
Material.
Material.
Which is like the perimeter kind of. It's like
We have a name for it when it's two-dimensional.
area.
Surface area.
Surface.
Oh yeah. That's what we want to do. Now this is one of the cases where we don't really have one input variable, obviously, because I'm thinking, well, they give me a volume. We're talking about surface area. This kind of harkens back to Algebra 2. So I'm going to hold off on that find one single. If you could find one single variable, nice, but obviously from the thing I just drew, we don't have one single variable. So I probably want to go the other way. So surface area, or I'm just going to call it A, that's the thing that I want. So let's write, what's step 3?
Write a function whose output.
Whose output is the thing I'm trying to optimize. So the surface area is equal to what?
It's x times y times 4.
Yeah, because there's 4 of them, right? We have 4 sides. One there, one on the other side, and one back here. So there's 4 total surfaces. Each one of those has an area of xy. There's 4 of them, so 4 xy's.
Plus 2x squared.
Plus
No, there's
1x squared.
Oh,
That's,
that's-
I know. And these are that's what's going to get you with this. And then the bottom, you only have 1x squared, so plus x squared. Step 4 would be write a constraint function. Are we given a constraint?
yeah.
that
So
the
let's have X
the volume
X
has to
squared times Y.
equal 32. So now step 5, use this to turn this into one variable. And so the volume is equal to what?
X squared times Y.
X squared times y. X squared y equals 32. And so we want to get this down to one variable. Which variable would we like to get it
Yeah,
down?
I think Y.
Get the y
So
by itself, so 32 over x squared. Use this to turn this into a function of one variable. So now a of x is equal to 4x. Y is 32 over x squared plus x squared. That's the same thing as 4 times 32 is 128 over 1x plus x squared. That's my function of one variable.
then we take the
We're going to take the derivative, we're going to set it equal to 0. Let me make sure I didn't mess this up. X squared plus 128 over x. Yes, okay. So, take the derivative, set it equal to 0. So, a prime, so that's 128 over x is the same thing as 128 times x to the negative 1. Take the derivative of that, the negative drops down, and then that becomes a minus 2. So that's negative 128 over x squared. Plus, what's the derivative of that? 2x. We took the derivative and we
set to 0.
set it equal to 0. So, hey, you see, notice we couldn't have done this one in algebra 2. Because how do you find, this is not a parabola.
Yeah.
So now we could do this, so that's pretty cool. So I want to do it this way, 2x equals 128 over x squared.
X squared.
There you go. So it's 128 over 2, which is 64. The cube root of 64.
4.
It is, good. I had to factor it out. But yeah, it is 4. Okay, and so now it says find the dimensions. Have we found the dimensions?
No.
Not all of them.
We need Y.
We need y. And I erased it, but you should always leave this guy up there. Okay, so we know that x is 4, so I'm going to plug him into here. 32, 4 squared is 16. This actually works out to 2. So the dimensions are 2 by 2 by 2. It often works out that way, right? Like maximize the area. Oh, it's a box, or oh, it's a square. You know, yeah. It would be different if there were a top on this box.
Yeah.
Yeah, right. I mean, it would have to be. Either you'd have a 4 here, I guess, and then that would have made that a whatever. I don't know. It would be different. It would just be different. Or would it? I don't know. No, it has to be different. Okay, so anyway, that's one thing you're gonna see. That was that. Okay. Here's the hardest question in differential calculus. In other words, or rather in first year differential, when you're doing, here's the hardest question I've ever seen.
Wow.
This will be extra credit, and you could get it to me. I'll give you.
Is this number 67? Or
No. This is an extra credit problem.
oh, so it's not.
I'm looking at the date. Today's date is the 9th.
Yeah.
And 1, 2. I'll give you 2 weeks.
23rd.
This will be due on the 23rd. This is from a math book, and I don't have the math. I know this problem so well that I could just state it. I don't know exactly how it's stated, but I'll give you the setup for the problem. In the book, it was not an odd numbered problem.
Oh.
Yeah, and so. Oh no, it was. You see the answer. That's right. You can see the answer, and you're like, how do you? That's the hard part. It said, and in it said this was on the entrance exam at Shanghai University.
Wow.
Okay, this is on the entrance exam. Here it is. You ready? And I'll go ahead and do step 1 for you so that you know what I'm talking about. Okay? The parabola, y equals 1 minus x squared. It's like that. We're only going to take the top half. Here's the problem. Actually, I'm going to draw this a little bit better. Okay, so here's the problem. Find the isosceles triangle. And isosceles, by the way, isoskilos, same legs. Okay? So that two of the sides are the same. Okay? That's isosceles.
Okay.
Okay, two of the sides are the same. Find a triangle whose base is on the x-axis and inscribes the parabola. So inscribes, meaning it touches right there.
Point.
It
Oh, at the inflection point?
inscribes it.
Sorry, no,
There's no inflection point there.
But like the
It touches, in other words, these are tangent lines. Tangent lines right there. So you're gonna, I wanted to say that. So to inscribe something can be said a little bit different. And we'll come back to this in a minute. Actually, and so what this is find the area, find the minimal area for this triangle.
oh,
Minimize the area.
because yeah, I guess there could be a lot. Of
Minimize
ways to do that.
the area. Because if you make it like way up there at the top, like this, you can make it arbitrarily large, right? If, as you imagine, you bring that point over and it goes like this and like this. If you're, you know, like 0.00000001 on this side, well, this thing is coming out like that,
Well, yeah.
right? So you could make the area arbitrarily large. We want to minimize the area. And I can tell you, it's not here. This one, the one that's tangent right there, does not minimize the area. It's somewhere between, and since you know that this is here at +1 and here's this at -1, this guy's at +1. I will tell you that this point right here is somewhere between 0 and 1. Now for the rest of your homework, there are a couple other problems that ask you about inscribing stuff. So this is extra credit, right there. Extra credit due on the 23rd. Number 23. Due the 23rd. Have fun. Have fun with that. That's probably the hardest optimization problem I've ever seen with one variable.
Did you get it right when you first tried?
It took me so long. It took me so long. I ended up finding a solution. Somebody online had done it.
Oh.
And I was like, and then I did the thing where I only read a little bit of it, and then once I saw the thing, I was like, that's what I messed up. Good luck. I'll tell you the answer too. I'll work this out and tell you the answer so that you can check your answer. Because you're gonna go, oh, it's this. No, it's not. No, it's not. I'll give you the answer next time. Or I might email it to you. I should have done that. I forgot to do that. Because I can't find my book, because we just moved. My book is packed up, and I would have just looked up the book. That's why I didn't write it out the right way. So I found the book. Here is the question. Number 17. It says, a version of the following exercise appeared on a 1999 entrance exam for Shanghai University in China. Consider the part of the parabola y equals 1 minus x squared, so that's that guy that I drew right there, from x equals -1 to x equals 1. This curve fits snugly inside an isosceles triangle with its base on the x-axis and one vertex on the y-axis. So, okay, isosceles means that those two are the same, and this guy might be the same if it happens to be equilateral. Equilateral is a special case of isosceles, but at any rate, this one is the same as that one right there. Then it says, This curve fits snugly inside an isosceles triangle with its base on the x-axis and one vertex on the y-axis. What is the smallest possible area of such a triangle? And here in the back, you can see the answer to number 17. Is 8 times square root of 3 over 9. Now, you might not get it that way. You might end up with this answer right there, and you go, that looks nothing like this, but it turns out that this, if you rearrange this guy right here, might as well do it since I have some time. This, root 3 plus 1 over root 3 is the same thing as multiply the top and the bottom by root 3, right there. That gives me 3 over root 3 plus 1 over root 3, which is the same thing as 4 over root 3. Okay, so then this is the same thing, 2/3 times root 3 plus 1 over root 3 is the same thing as this right here, which is the same thing as 2 times 4 is 8 over 3 root 3, which is how you get that. Multiply the top and the bottom by root 3 to get 8 times root 3 over that guy is 3 times 3, which gives us the answer that it gives you in the back of the book right there. So good luck with that one. Now, here's the thing, number 21, and I'm gonna give you, this is one of your homework ones. And so pay attention. This says, find the dimensions of the rectangle of largest, find dimensions of rectangle of largest area. What are you trying to optimize?
Area.
So you want a function whose output is?
Area.
Okay. Find the dimensions of the rectangle of largest area which can be inscribed in a circle of radius R. Now, you're not tangent to inscribe a rectangle in a circle. I'm just going to think, okay, here's a circle of radius R. Why don't I center it at the origin? That'll probably make my life easier if I go ahead and do that. And so what they mean, the rectangle of largest area is one who just touches at 4 points. That's what it is to inscribe that guy. Now let me give you some hints on this. First off, don't assume it's a square. It might be, it might not be. So we're not going to assume it's a square. And one thing to note, and you should use this everywhere, in fact it would probably behoove you to use it here too, is to say, you know what, this is symmetric. Like all of these are symmetric. And what I could do to find these dimensions, because that's what it's asking for, it wants to know this value, let's call it big capital X, and it wants to know this value, big capital Y. What I could do is just say, you know what? If I just look at this part right here, it's got to be symmetric everywhere else. And so what I could do is say, yeah, I could just go, okay, well, let me set it up this way. I'll just look at the first quadrant. I have some function. You should be able to write what that function is. It's a circle of radius R. Yeah. Right? And so what you have then, you're not going to assume these are the same, but you have one of these and one of these. And this is X, so this length right here is X. We'll call this length right here Y. And then it's, once you figure that out, then you could say, well then this Y that I'm looking for is actually just two of these Y's, right? Like from here to here is little y. From here to here is also little y. It's got to be symmetric, right? This is x and this is x. So the x that you're looking for would just be two little x's. The y that you're looking for here would just be two little y's, like that. Does that make sense? Yeah. You forget about this problem. You work on this problem. Get your answer for x and y, finding the largest area, so you're maximizing area. In that case, what would it be for for area. Area equals,
Y times F.
yeah, there you go, right? Now it's just now, is there a constraint? Is there a way I could get y in terms of x or x in terms of y? We have a function there. Right? Isn't that a function? You should know what the formula for that is. Right? And so that's how you do that. Take a derivative, set it equal to 0. And so your constraint in this case is that y, you have a function. Like y equals something in terms of x. And you do all of that right there. And then you bring it over here and say, well, since I found it for there, it works everywhere here. And so 2 times whatever that value is, and 2 times whatever that value is, are the dimensions that I'm looking for. Now, if the problem said, instead of find the dimensions, if it just said, what is the largest area? Well, you get to this point and you find your x and you find your y and you plug it in and you get your area for there, and then what would the entire area be? If this is A, then that's A, and that's A, and that's A. It would just be, then the final area that you're looking for would just be 4 times A. We're going to do that a lot in later this year when we do integrals, integral calculus. You're going to have a lot of problems like this with area, and it's going to be like, well, you know what, instead of doing all of this, let me just chop it up, I'll do this amount right there, then I'll just multiply it by 4, and I'll have my final answer. So there you go, that's all I have today. This is, oh, and here's your homework. Here, you're missing a few, you can get it to me whenever. This is going to be hard. Please email me when you inevitably run into a problem. No, I didn't say this, note 53, it's just A. You could do B if you want, I don't care. But just A. I hope you guys made note of that. This is going to be hard.